Hello, this is the seventh in a series of recordings about reaction dynamics for the module 30,042. And so today we're going to continue talking about transition state theory. We're going to talk about two real strengths in transition theory, talking about kinetic isotope effects and tunneling, because both of these, the way that transition state theory treats the reactions leads nicely into to these effects being sort of a bit more easily explained. For further reading, again, I've linked to the reaction kinetics textbook, and again, this QR code that's right in front of you that leads you to that textbook. So, as a reminder, that one, you can get access to it via that link, but that access will only be free for a couple of weeks. So, hold fire on doing that until you absolutely have to. I would suggest sort of a bit later on, once we're finished and you're just revising the content. Okay, don't forget you can always email me any questions, so just as a reminder, please do. Okay, but let's get moving. Okay, so when we're talking about kinetic isotope effects, we're talking about these sorts of reactions here. So, in this case, we've got R1 plus H, so it's with a hydrogen attached to it, plus R2 is going to give us R2H plus R1. All right, so this is like an acid-base style reaction, and you get the same reaction with a deuterium version, a deuterated version of it. In this case, of course, what's happening is the deuterium and the hydrogen are being exchanged between R1 and R2. And the key point about kinetic isotope effects is that these two reactions are often observed, or similar reactions like this, are often observed to have very different rate constants. Now, a bit of terminology here in terms of kinetic isotope effects. There are several different types, so primary, secondary, etc. The key point is in this lecture course we're going to mostly be talking about primary kinetic isotope effects, and these are noted when RH or indeed RD is broken or formed, broken and formed in the rate limiting step. So in this case here for these two reactions, you can clearly see that this bond is being broken in the rate limiting step, and this bond and it's being formed here. So this is going to be broken or formed in the rate limiting step. Okay. So, in terms of reaction dynamics, it's important to realize when you look at the potential energy surface that the shape of the potential energy surface for both of these reactions, so regardless of whether you've got a hydrogen or a deuterium, the shape remains the same, but the things that change are the energies. Okay, now and in particular this E0 value in the Eyring equation. Okay, so if you just remember, E0 is this difference in energy between the reactants and the products, okay, of the equilibrium process that transition state theory puts in, okay, and that equilibrium process is between the reactants and the transition state. So the reactants are the reactants, so it'd be these things here in this case, and the products would be the transition state. Okay, so that's the energy of the transition state, and this would give us this E0. So this is the difference in energy between the reactants and the transition state. And in particular, a little bit more detail, and I kind of alluded to this in a previous lecture but didn't specifically say it, it's actually the difference in the lowest occupied energy levels in the reactants and in the transition state. And the way we can figure out what these energies are using minimum 0 point energy. And the key point is that what we want to do is we want to know what the difference in 0 point energy between the deuterated version of this reactant and the hydrogenated version is. Now, when we're trying to figure that out, when we're trying to figure out what the minimum energy is going to be, of course the R groups are the same in both cases, and it doesn't matter how many bonds they've got, it's still going to be the same in both cases. The difference lies in the bond with the deuterium and the bond with the hydrogen. That's where the difference is. And so when we want to sort of work out what the difference in 0 point energy between the two things are, we can just basically only consider those bonds. And so for the rest of the lecture, that's what I'm going to be doing. I'm just going to be talking about those bonds in particular. Okay, so if we've got an equation here for the 0-point energy, okay, so the 0-point energy is given by, you know, Planck's constant times by the frequency of vibration of that bond, so it's either the frequency of bond vibration of Rd or Rh divided by 2. Okay, and of course you know an equation that gives you that can give you the frequency of vibration of a bond. And of course, if we want to find out the difference between these two, we actually want to find out what this would be in the scenario where you've got the frequency of vibration for the Rh bond minus the frequency of vibration for the Rd bond, and that would give us, you know, EZBE for the hydrogenated version minus the deuterated version. Okay, key point to use in this equation is that everything stays the same, including the force constant, apart from the reduced mass here, which of course changes, and that's because you're changing from H to D. Okay, so on the previous slide we said that essentially what we've got is that the biggest kinetic isotope effect is going to be noted for H versus D, and we're looking at this kind of this reaction of RH you know, is essentially in equilibrium with a transition state, and also RD is in equilibrium with a transition state. And in our case, it was, you know, R1H and R1D is in equilibrium with transition state, and that goes to, you know, R1, R2D and R2H. Yeah. So in this case, we've got R2, and in this case, we've got R2 again. Yeah. Okay, so these would be the two equations we're looking at, and you know, so we really what we want to do is we want to look at the difference here. Okay, so what we can do is we can say, well, what is the difference in the reduced masses? Because this will feed nicely into that equation for the frequency of vibration that we had a second ago. And I'm just going to erase this stuff just so that it doesn't get in the way of some of these equations, and so I can use it again. So yeah, we've got this ratio of reduced masses. Yeah. Okay. Just get that. Yep. And the key point here is that the ratio is given by, you know, essentially RH versus RD, and so we can just put the values in here. So this part is the reduced mass for the H, and that's on the top, so that's shown this way around. And this part here that I'm going to draw in blue is 1 over the reduced mass for RD. Okay, and because it's 1 over because it's on the bottom of this ratio, isn't it? Yeah. So that's what that is. And then what we can do is we can start making some approximations. First approximation, of course, we can do is just get rid of these two because they're going to cancel, isn't it? Yeah. So our two, you know, our two MRs are going to cancel, and so we're going to end up with MH over MD here. Yeah. Because they're the same. But the other thing we can do is we can say, well, you know, if our mass of our R group is much bigger than the mass of deuterium, or indeed the mass of hydrogen, then in that case, this expression here is equal to 1. So, you know, the way we can think about this is, you know, let's just pick a mass. Let's say, for example, our R group is even a really small group, like, you know, an ME group. In that case, the mass is going to be 15. That's 15 plus 2 over 15 plus 1. That's 17 over 16, which is pretty close to 1. It's a little bit more than 1. We're not going to be massively inaccurate by assuming that it's equal to 1. And of course, that's one of the smallest R groups. You know, if this was a benzene unit or something else, it would be much bigger. It would be much greater mass. So this is a valid approximation. So essentially what we can do there is we can say that this cancels 2 because this is equal to 1. Yeah. So we get left up with this part here. So we get, you know, the ratio of the reduced mass is equal to the mass of the hydrogen over the mass of deuterium, which is equal to 1/2. Which is nice and simple. And of course, you know, what we can say is we want to get the ratio of the frequencies of these, you know, and I'll show you why it is we want the ratio in a second. But effectively, you know we can probably get the frequency of vibration for the hydrogenated version because, you know, we can do IR, can't we? Or in most cases, these are bonds that are known. We might not know the value for the deuterium, but if we know the ratio of the two, we can calculate the deuterium one from the hydrogen one, can't we? So we do the ratios. We can basically put, you know, the Now this kind of explains why we needed the ratio of reduced masses, but we've got the reduced mass for the RH on here, got the reduced mass for the RD here. If you simplify this equation, everything cancels apart from these two, so we get left over with the square root of the ratio of the reduced masses. And note that this is the other way around, so it's these two are the other way around here. Yeah. Okay, so in other words, the reduced mass of RD over the reduced mass of RH is equal to 2, so the ratio of the frequency is equal to √2. Okay. Key maths rule that I used in order to simplify it was this bit here. Okay, so again, if you want to follow the maths through, then feel free to do so, and that's the rule you're going to need. Okay, let's keep on trying to develop this further. And what we've got from the previous slides, we've got a ratio of reduced masses, mu RH over mu RD is equal to √2. Yeah. Okay, so if we know what this one is, then we can calculate this one, can't we? We can basically say that URH is equal to mu RD √2, or √2 mu RD. Yeah. Okay, so that's what we're trying to do there. Okay, in order to do that, however, we're currently in units centimeters to the -1, and as you remember from your first year spectroscopy, you don't really want that unit. That's not a very useful unit. It's certainly not SI, and so what we need to do first, we need to convert it to per second or hertz. And in order to do that, we need to multiply by the speed of light in centimeters per second. Okay, so centimeters per second. So we can do that, and we end up with this result here, which I've just written all over, and I'll just get rid of this bit so you can see it. So it's 8.97 times 10 to the 13 per second. I'll leave that bit of equation in there because it'll be useful. Okay, and then what we can do is we can say, well, wait a minute, we have an expression for our 0 point energies, okay, and we can say that the difference for the reactants in the 0 point energies is given by the 0 point energy of one of them, so the H version, and the 0 point energy for the other, okay, so the D version. Yeah, and so if we do that, we can basically say that this is H over 2 mu CH, and this is H over 2 mu CD. And so, if one minus the other, we can take the common factor out, and it's just going to give us that. So we need this, the frequency of vibration of the CH bond minus the frequency of the vibration of the CD bond. And of course, we can calculate that out by putting this in place of one of these, essentially. Yeah. And so what we do is we put the numbers in. So we calculated this a minute ago, and we could put these numbers into this equation, and we end up with our answer, which is about 8.7 joules per molecule. And of course, that's joules per molecule. It's not per mole. We want it in per mole because that's a convenient value that we sort of know for comparison. And what we can do in order to do that is we can multiply it by Avogadro's number to get rid of the sort of per molecule, as it were. And just basically bring in per mole, and to make it per molar, and then per mole, not per molar, sorry. So in that case we end up with about 5 kilojoules per mole. Okay, so why is this important? Well, what we've done so far is we've basically calculated out the value of this gap here. Okay, so we've got these two values here, and we've calculated out, this is our sort of delta EZPE. Yeah, okay, so that's the value we've calculated out so far. Now, if you remember, we've sort of seen this kind of diagram before, because I used it when I first introduced transition state theory, because basically the whole point of the Eyring equation is this E0 in the Eyring equation is given by the difference in energy of the reactants, which is obviously the reactants, and the products of the equilibrium. So the products of the equilibrium is the transition state. Okay, so this is given by the difference in these two energies, which is a bit like an activation energy. But this is these differences in energies for the H version and for the D version are depicted by these arrows. Okay, now the whole point is really that then we can make predictions if we know this delta EZPE for our reactions. Okay, now if in the transition state the difference in 0 point energies was the same, so it's roughly where I'm putting the line here, then this arrow would go a little bit further up, and these two arrows would be the same size. Okay, so if they were the same, we'd kind of be saying, well, probably the bonding's about the same in the transition state as it is in the sort of the molecule at the beginning, particularly for RH. The bond probably won't have elongated very much. Okay, that would be the condition under which it would be the same, in which case our E0s for both the hydrogenate, the one with the hydrogen, the reaction with the hydrogen, or the reaction with the deuterium will be pretty much the same because the arrows are pretty much the same size, in which case we wouldn't get a kinetic isotope effect. Okay, now what is more likely to happen, however, is that in the transition state, and at this point in time, I just think back to those potential energy surfaces. Yeah, the potential energy surface showed that the transition state, the bonds in the transition state were more elongated than they were for equilibrium bond distances for either of the two molecules. Okay, particularly when the transition state was somewhat in the middle of the diagram and not late or early. Okay, so the scenario is a bit closer to what I've drawn here, where the bonds are longer. Now, you can think about an extreme of that sort of bond length, where essentially what you've got is you've got R, and then you've got H, pretty much R dash. Okay, and these are much closer together, near to near to equilibrium bond distance for H to R dash, yeah, but RH bond is fully broken. Okay, and likewise the same thing, for D would be the same, yeah, it would be the same because it's the same mechanism. Yeah, in that case, then because these bonds are pretty much broken or entirely broken, then the transition state is actually R plus D R dash, R plus HR dash. Okay, or it's very close to that, because the bond's pretty broken. Now, if that's the case, then the basically the energies of the transition states are going to be pretty much the same, because this is the transition state here, R. Okay, and in that situation, essentially what you've got is that these lines would overlap. So instead of my green line being where I've drawn it here, it would instead be basically on top of another one. Okay, and in that case, these two arrows, the difference in the size of these arrows is going to be given by the delta E ZPE. Okay, so that sort of difference in 0 point energies of the reactants that we talked about so far. Okay, and of course, for the example we've been going through so far for H and D bonded to carbon atoms, then that difference is given as 5 kilojoules per mole, or 6 times 10 to the minus 21, I think, joules. Yeah, or whatever the previous answer was. Now we can express this mathematically, of course, and same sort of idea. Basically what we said here is that the energy, the E0 is epsilon 0. Epsilon, by the way, is being used when it's sort of molecular units. In other words, this would just be in joules. Of course, we can convert that to molar units, joules per mole, kilojoules per mole, by dividing by multiplying by Avogadro's, by multiplying our epsilon value by Avogadro's number. But I've done it, just using epsilons here. You could easily do this with capitals too, it'd still be true. This is our energy of the transition state. This is our energy of RH. So this is basically saying that the length of this arrow, this arrow here that I'm now ringing again, is equal to that. It's a mathematical expression for what we've shown on the slide. And likewise, you've got the same expression for D, and that then we can say, well, the difference in the sizes of these is basically going to be given by this part minus this part. And I've put this together here and then said, essentially, well, if this one and this one are the same, then essentially this will drop down to this is equal to that, which is the same as delta E ZPE for the reactants, okay, that we calculated already. Okay, so key point here is that we can get some insight into the mechanism, because obviously if we measure the two rates and we find that the activation energies differ by 5 kilojoules per mole, or roughly 5 kilojoules per mole, for the scenario where H and D are connected to a carbon atom, then in that case we know that the transition state is fully broken, or pretty much fully broken in that transition state. So the CH bond or the CD bond is fully broken in the transition state. Of course, if it's closer to 0 kilojoules per mole, then we know it isn't. Okay, and again, we can also relate this back to potential energy surfaces, and we can understand reactions a bit more by doing that. And one thing I'm going to get you to do in the problem sheet is exactly that. Okay, so of course, if we know there's a difference in our activation energies or our E0s or our experimental activation energies, then we can calculate out, if we basically put in place of this, we put E0, which it's not perfect, but it's a similar idea. Then what we can do is we can calculate out the effect. We're basically saying, in order to do that, we want to get a difference in the rate. We can just put the activation energy, or E0 for the H reaction, activation energy for the E0 for the D reaction, and if we simplify this equation, we end up with this. Okay, so this is the deuterium one minus the hydrogen one over RT, and that will give us the ratio in rate constants. Okay, so the ratio in rate constants is given by this delta here, and of course this is going to be related to ZPE, yeah, delta E ZPE, and in this case I've used capital E to indicate that we've got that in joules per mole. Okay, of course, what we have to do in order to use this equation, we have to assume that this part is equal to 1, so we can cancel it, which is probably not a good assumption, but at the same time it's an assumption we can make here. And we can then say that the delta, the difference in these two, is equal to 5 kilojoules per mole, and so therefore we end up with, we need to make that back into joules per mole so we can cancel the units, but essentially that means that our ratio of rates is going to be given by about 7.5. So the reaction with the hydrogen is going to occur 7.5 times faster than the reaction with the deuterium, okay, because KCH is equal to 7.5 times KCD. Okay, yeah. So I just wanted to go through a quick example of this and show you how you might do this. I'm going to skip a few steps here because we already did some of the calculations, but I will show you sort of what we can get from this basis. So we've got two reactions here, and they're exhibiting a kinetic isotope effect, and obviously the differences are there and there. Yeah. Okay. So you can see what's going on. We can of course experimentally measure our rate constants. Yeah. And we remember this bit. Now, what we want to do is, if we've got this equation here, we can basically log both sides. So if we plot log of this versus this, then we just get rid of the exponential, don't we? Yeah. So we can plot this versus 1 over t, and this is going to be our slope. Okay. And if we do that, what we can do for this reaction, because we were able to measure our rate constants experimentally, it was found that our difference in 0 point energy was 4.3 kilojoules per mole. And this is a CH bond or a CD bond that's being broken. So the theory would say, theory says that it should be, theory is 5 kilojoules per mole. And experiment is 4.3 kilojoules per mole, and so therefore we can say that it's not perfectly fully broken, but it's very, very close in the transition state. So once again, we can use this to explore mechanisms, and we'll do more about this, in workshops, but also in some of the quizzes and that I get you to do as part of this. Okay. So the key point is that if there's an RH bond in the RN limiting step, we're going to expect a KIE. Another important point on this graph is if actually we don't use this equation here, but we use the previous equation, which involves, where we've got essentially our H and our D here, essentially put in, then, we've obviously assumed that ratio is going to be 1, and so therefore, this expression should go through 0, because log of 1 is 0. It might be that that's not actually 0, and so we can actually use that to sort of understand how close that is to being correct, but also we can compare it to calculations using transition state theory too, to figure out whether we can get close to H and D values for our pre-exponential factors. Okay, so we're going to finish off this screencast by talking about the final topic in this area, which is that of tunneling. So tunneling relies on the quantum mechanic idea of there being a finite probability of the wave function particle appearing at the other side of finite potential energy barrier, which is what it says here, right? And what that means in the context of reaction dynamics and in terms of reactions anyway, you've got your energy barrier, which is your sort of activation energy, And tunneling says that there's a potential that the molecules might just skip that barrier in its entirety and just appear at the other side. Okay, so that's the idea. Now, obviously that's not going to happen for every molecule, and when we talk about a finite probability, what we mean is, it can happen. We don't mean it's massively likely. Okay, so few things that might make it more likely. One of which is the use of lighter elements. So for example, if you are running a difference between, a reaction that has got a lot of H in it, so this one is a good example, right? The difference here is going to be pretty big because of tunneling, okay? Because it's H versus D, and that's a very big difference in weight, essentially. Okay, and the key point is that light elements will tunnel more efficiency. And the thing that tunneling does, because of this additional route, which is obviously lower energy and therefore more easy, is that it will mean that, for example, for hydrogen versus deuterium in this case, hydrogen you'd expect to see an increased rate. Particularly at lower temperatures. So lower temperatures is this part of the graph, isn't it? Because it's 1 over T. Okay, an increased rate at lower temperatures versus the kinetic isotope effect that you'd already expect to see anyway. Okay. Okay, so just to conclude this screencast, we're just going to finish off talking about transition state theory. Key point is that transition state theory allows for molecular complexity, and so in that respect alone, it builds on collision theory. It gives the same answers to collision theory when you haven't got a complex molecule, but we can account for molecular complexity, and it can, in many situations, give a better estimate of the pre-exponential factor, particularly in those unimolecular cases. And finally, it provides some idea of various phenomena such as, temperature dependence. It allows actually for a greater range of different types, in terms of equations, temperature dependencies versus, say, for example, Arrhenius theory, which basically says the pre-exponential factor isn't temperature dependent, and of course collision theory, which says it's the pre-exponential factor is proportional to temperature, to the square root of temperature. Okay, so transition state theory allows for a greater range of different results there. And also transition state theory will explain kinetic isotopes effects pretty well. Okay, of course the main issue with transition state theory is this point here, this inability to probe the transition state, because the transition state is so short-lived. Okay, we can't get some very good information about the transition state, and that limits our ability to use the Eyring equation in the form I showed you. The other issue with transition state theory, even if you can tweak it to improve it, is that the bigger the molecule, the more computationally complicated that gets. So if you're actually trying to use correct ways, if you're trying to compute partition functions, rather than just doing the simplifications we did, if you're trying to do that, transition state theory becomes really difficult for more complex molecules. And of course, we can gradually improve on it over time, and people are doing this, but really, this is still ultimately holding it back from being able to predict any reaction, and that's definitely the case. And the final point is, of course, this potential energy surface and the fact that these are very powerful in allowing us to understand reactions. So thanks very much for listening, and that's the end.